Hello and welcome back to Introduction to Machine Learning. I'm Ludwig Botmann, and in this video I will tell you about supervised classification in a nutshell. In the end, you should understand the basic concept of a classifier. You should know the concepts and differences between probabilistic and scoring classifiers. You should know about the distinction between discriminant and generative approaches, and last but not least, I hope you will understand the basic ideas of logistic regression and of naive Bayes. Classification tasks. We want to learn a function that assigns categorical class labels to observations. So if you remember the regression chapter, there we tried to predict a numerical target variable. Here the target is a categorical variable, and each observation belongs to exactly one class. The task can contain two or multiple classes, but each observation only belongs to one class. So we have a very similar visualization here for the learning process as we had for the regression task. As an input, we have labeled training data, which are divided into a feature matrix X and a label vector Y. In this case, the label is the level of happiness. This target variable has three classes: not too happy, pretty happy, and very happy. And in this very small data set, each observation belongs to a different class, but of course in a larger data set, one class can have various observations in it. So then we try to learn something with, for example, later on the logistic regression or the naive Bayes approach. And as an output of the learning, we have a classifier. At prediction time, we have unlabeled data, which means all the target variables are question marks, basically, and we try to predict the class of these feature values over here. For this, we'll take the classifier, and as final output, we have the level of happiness, which can have three classes, and in this case, two observations have the same predicted class. Let's start out with some basic definitions. For every observation, a model outputs the probability or the score of each class. So probability has always to live in the interval 0, 1, and a score may be from R plus, let's say, perhaps from R0, but basically score, it may be from the entire R, so just any real number. In a multi-class case, the class label is then usually assigned by choosing the class with the maximum score or probability. So let's directly jump to the example here. We have a prediction for some unlabeled data. We do not know the level of happiness. The first output of the classifier will be such a probability or score vector. In this case, it's a probability vector. So these three numbers here add up to 1. You can check the math, that works out. And of course, we have to decide for one of the three classes here. And I think the most straightforward way is to just assign the class with the highest probability. Okay, so we have a probability of 0.4 for not too happy, a probability of 0.35 for pretty happy, and a probability of 0.25 for very happy, which means, okay, basically not too happy seems to be the most likely class, even if it's only 40%, but it's still more likely than the others, so the assigned label is not too happy. We can of course do the same thing if we have just two classes, but for just two classes we can also decide based on some threshold C where we go. So we might have then just two probability predictions, 0.6 and 0.4, and usually we just cut at a threshold of 0.5 and then take the class which is above this threshold. Okay, That was the difference between multi-class and binary classification. Now let's speak about the difference between discriminant approach and generative approach. These are two very different, fundamentally different approaches to construct a classifier. Let's start with the discriminant approach, where logistic regression, okay, there's a typo, is one example. The discriminant approach always asks, what is the best prediction for the class given these data? Okay, so we try to find something like which class given the features is most likely. So perhaps we try to find probability of this, P of y given x. On the other hand, the generative approach asks a different question. That is, which class tends to have data like these? So one example is the naive Bayes approach. So we ask ourselves more, what's the distribution of x given some class? Y equals y. Okay, so it's different probabilities that we try to model here. And yeah, two examples here are logistic regression and naive Bayes. Logistic regression has the nice property that it's kind of linear in some sense. So not in all the senses, but I will tell you in which sense. So this decision boundary here is a linear function. So we have feature x1 and x2, two classes 0 and 1, and the estimated decision boundary is always linear in logistic regression. This is not the case for naive Bayes. For naive Bayes, we might have in a very simple case also linear decision boundary, but it may be somehow an ellipsoid or a parabola. Yeah, this is the decision boundary. The decision boundary is just exactly the points where all the classes have the same probability or score, so where we do not really know in which class we want to put those. And decision regions are then everything on the two sides of those, of the decision boundary. Okay, so decision region is everything which belongs to class 1 or everything which belongs to class 0. Okay, that's discriminant versus generative approach. Now, as last two steps of this video, I will tell you about logistic regression a little bit more in detail and about naive Bayes also a little bit more in detail. Logistic regression, as already said, is a discriminative approach, which means that we try to figure out the probability of y given the features. It's somehow linear. So as I told you, the decision boundary is a linear function, and this stems from the following system here. So let's see what happens with an unlabeled data point at prediction time using logistic regression. So we have this unlabeled data point here, two features and a class which we do not know about. So what the classifier does first is computing a score, and this score is a linear function, a linear combination of the features. So that's exactly what we have seen in the regression chunk on just the usual linear model or the ordinary least squares estimator, which estimates this model, but we have the exact same function, theta 0 plus theta 1 times x1 plus theta 2 times x2. So this is a score. The score lives on just the real numbers, so this can be anything between minus infinity and infinity. And in this case, let's say the score is 1.2. Okay, just a number here. We still don't know the class. And what we can do for obtaining the class, or what the logistic regression does, is the following. It applies this function here, exponential function of the score divided by 1 plus exponential function of the score. That's exactly what you see here. So this S-shaped function is exactly exp of 1 exp divided by 1 plus exp. So what happens is that all these numbers, these real numbers, are squashed into the interval 0, 1. So you can try a little bit around, plug in any numbers, you will not be able to get a result outside 0, 1. So in this case, the score of 1.2 leads to a probability of 0.7685. and we still don't know the class, but then we can apply some threshold. Let's say if the probability is above 50%, then we just say it's class 1. Okay, let's clean up a little bit. This here is the threshold. This may be 0.5. It's always a very easy first choice. Everything with a probability higher than 0.5 gets class 1. Everything below 0.5 gets class 0. And that's basically what logistic regression does. Now the only remaining question perhaps is, how can we find these parameters theta 0, theta 1, theta 2? Okay, perhaps let's just use empirical risk minimization as before, but we will speak in depth about this in another chunk. Okay, so that's it about logistic regression. Now, as last example of a classifier, of a learner that puts out a classification machine learning model, we speak about naive Bayes. Naive Bayes is now a generative multi-class approach, which means, first of all, so the generative part means that we try to estimate the distribution of the features given the classes. The multi-class approach means that, well, the target can have more than just 2 classes. Logistic regression, on the other hand, is just able to work with binary target variables. Okay, what does naive Bayes do? We have to estimate 3 types of distributions. That is the marginal distribution of x, the marginal distribution of y, and the conditional distributions of x given y for each class. Okay, so basically pi of x given y is not just one distribution, but we need it for pi of x given y is 0, for y, and so on, depending on how many classes we have. Okay, let's perhaps have a look at the visualization here. We take a very simple example here. We have just one feature and one target variable. The feature is health. Health is a categorical feature. It has 4 classes: poor, fair, good, and excellent. That's the 4 options you have for health in that example. And the level of happiness is the target variable. This can have 3 classes. These are not too happy, pretty happy, and very happy, just as before. Okay. Now what we do is, first, we have to estimate the marginal distribution of x, of the feature, which is health here. So on the y-axis we have just the percent in the training data, so it's really just empirical distribution here. And for each of the 4 classes we have the ratio of observations which have as a feature exactly that class. We do the same thing for the distribution of y, so the distribution of the classes. We have the 3 different classes here, and on the y-axis again the ratio of these classes in the training data. And then a slightly more complex part is the third part. That's the distribution of x given y, so in this case distribution of health given the class not too happy. Then we have again all the 4 classes of health level, but we would have to do this not only for the class too happy, but also for pretty happy and very happy, so which would mean that, well, we would have 2 more bar plots here. But let's not make it more complicated than necessary here. So that's the distributions we estimate in the training process, and that's basically all we need for the classifier. Now we take these distributions and at prediction time do the following. So we have an unlabeled data point, a person which has a fair health. And now we want to know how likely are the three classes not too happy, pretty happy, and very happy. And on this slide, I will only show you the computations for the class not too happy. But for the other two classes, it's the same system, let's say. Okay. So the distributions that you see here are exactly the same distributions as on the slide before. But now we have highlighted some of those bars in the bar plots, which refer to the classes we need right now. Okay, so in the first plot, health equals fair is important for us because the observation we try to predict has a fair health. So we take this 18.6%. Then we wanted to know the probability of the target happiness level equal to not too happy, which is 12.55%. And as a third number, we need the conditional probability of health given the class not too happy. So in this case, class fair given the class not too happy is 31%. Okay, now we have three numbers. What do we do with that? Let's clean up first. So the question is now, and you already see the solution, it's 21%. Okay, the question is now, what is the class probability of not too happy given health fair? Okay, the class probability of not too happy marginally without knowing anything about the health level is 12.55%. Okay, that's a baseline, we start with that. Now the question is, does having a fair health increase or decrease this, we can also call this prior probability? And what we do for answering that question is that we compare two numbers, and these two numbers are the probability of having a fair health and the probability of having a fair health given the class not too happy. And what we see is that given the class not too happy, the probability of having a fair health is higher than overall, than on average, than marginally, which means that if I know that the person has a fair health, that then this probability should also be higher, so the conditional probability of not too happy given health fair should be higher than the marginal probability of happiness level not too happy. Okay, so that's the basic intuition about this. We have a baseline that's 12.55%, and we try to figure out if the information that we have about that person increases or decreases that baseline. In that case, it increases the baseline. Here is the math for this. So what we do is we divide those two numbers, so this number and this number, we divide those by each other. And we see, okay, 31% is higher than 18%, so baseline is increased. We multiply this with the baseline, and then we get some class probability given the data. So this is now a probability of not too happy given health is fair. That's 21%. Okay, and we can do the exact same thing with the probability of pretty happy given fair and of very happy given fair. And then, well, then we have three numbers, and as a final prediction we can just choose the maximal number.